because I might ask you to solve for moles. So let's say a gas sample. Now this is a little different than what I'd ask in a limiting reactant problem, but it's getting to the people at MIT. Gas sample, let's see, is held at, say, 20 degrees C in a 0.50, now let me do this. In a 50 ml container at a pressure of, say, 864. How many moles? Again, I'm making up these things on the fly here. It would have to be a pure gas sample, first of all, but everything we're dealing with in this section right here is all pure gases. When we go into Dalton, again, the partial pressure thing, that's when we start to talk about mixtures. So I look at all, what do I got? I got temperature. What's that, 20 degrees C. Well, I'm going to be proactive. That's 293 K. I got a 50 milliliter sample, so volume equals 50 ml. Now, right now at this point, I don't know if I have to convert it into liters or not. I'll just wait and see what I got. I keep reading, and it says it's got a pressure of 860 torr. And again, I don't know if I need to be in standard units or not, because I don't know if I'm in before or after conditions yet. Then they want to know how many moles are there. So right at this point, I'm done reading the question, and I can see, well, this is not a changing set of conditions. And so what I'm going to be solving for is PV equals nRT, or N equals PV over RT. By both sides by RT, both sides by RT. And once I see that R is involved, now all my units got to be in proper units. So if I'm in proper units, got to get rid of milliliters, go to liters. Liters 1.001, 50 liters. Torr, let's see, 1 ATM, 760 torr. Let's see what that is. So 860 divided by 760.
1.13.
Thank you. 1.13 ATM. Okay, now I'm good to put stuff in here. N equals the pressure of 1.13 ATM. Volume is 0.050 liters. R, 0.08206 liter atmosphere Kelvin mole. Temperature 290 degrees. Okay. And equals 1.13 times 0.05 divided by 0.08206. Hello. So this is the sample of 0.0023, I don't know, maybe one more, 235 moles. I don't know what the gas is. So think about it like this. That can serve as a good starting point for a limiting reactant problem. Right? I give you all the information to get the moles, now that's a moles half. I could give you a mass. What if I gave you a mass? What would you do? Multiply by? If you wanted moles. We're at what? Star grams. So in a limiting reactant problem, I could just say you have a mass of this. Or I could also give you that you had in some of the problems, I gave you a pure liquid in its density. And that lets you get the moles, right? Because you get the mass, right? So for example, if I said you had 50 ml of some substance X, and its density was, I don't know, 1.7 grams per ml. then I can take this times this, get grams, turn it into moles. I'd have to tell you what X is. Does that make sense? Your flow chart has all those different inputs, remember that? So I suspect that this would be a bigger problem.
Well, we would need two to actually do the limiting.
Yes, you'd have to have another thing. So yeah, so I'd have to tell you like something about this substance and then something about another substance. I would give you a balanced chemical equation, so that would be another tip-off that you're dealing to with this living reactant.
If we're given moles in like a problem like this, but they're asking us to find, you know, the volume.
Yes.
If it's in like a balloon or something.
Yep.
We would just isolate volume.
Yep.
And that,
Same thing as you do with any other, yeah.
How do you know that it had to be in like that?
If I'm dealing with PV equals nRT,
Always gonna be in atmosphere liters.
yep. And it's again because that number has the units liter, atmosphere, Kelvin, mole.
It's like
Yep.
cancel.
Yep. Yep. What are we doing? It's all up to you, whatever we want to do. I feel like hell.
If this was a limiting reacting problem, you would
Yes.
give us another one and say, here it is. You'd have to find out and then you do the
Yeah, I would give you enough to get the moles of another reactant, whether I give you another set of PVT data, or I give you a mass of a substance, or I give you the volume of a pure liquid and its density. Okay, if I gave you any of those, then you have two sets of that, right? Again, they don't have to be the same. They don't all have to be both be PV and RT. One could be one could be mass. But I give you those two quantities and I ask you for how much of a product, then yeah, you got a limiting reactant problem. Figure moles have, turn into moles need, take your limit, go to your product.
can we go over more mass problems?
Yep. Let's do this one that was in your book. Okay. I'm going to do this one. This is probably a little trickier than I would get on the test if this was a density problem. But this one was a homework problem, a little trickier.
Would this be like a what is the identity of the mass or of the gas?
Could be. It's a possibility. Here's one that was in your homework, 62. And I'm just going to read it and we'll just write things down. 62, again, a little more complicated than what you're going to get, so don't freak out when you see this, but it was a homework problem assigned a while ago. It says a compound has the empirical formula CHCl. So, empirical formula is CHCl. Continue to read on. A 256 milliliter flask. That sounds like a volume to me. 256 milliliter flask. At 373 Kelvin. 373 Kelvin. 373 K. And 750 torr. Pressure equals 750 torr. Contains 0.8 grams of the gaseous compound. Well,
15.7.
yeah. And they want to know what the molecular formula is. So this one looks kind of tricky, doesn't it?